Hey folks, Michael here, and today we'll be discussing metastability. What it is, how it works, and why it screws up our digital logic. So metastability, it's this big mystery when you're first learning it in undergraduate, and I never fully understood what metastability was until after I graduated. So I'm here today to debunk the mystery and hopefully help a couple of you out going through undergraduate. So metastability, we're going to be taking a conceptual approach. We're really going to nail the concept of it down, and we're not going to worry too much about the math behind it. So let's take a peek at what we'll discuss. So we're going to discuss the understanding of what causes metastability in digital logic. What conditions will bring about metastability? And that's just kind of violating the setup and hold time. And you've heard about that going through undergraduate. We'll then dig a little bit deeper into the D flip-flop. We'll take a peek at the transistor level understanding of how the metastability propagates through the flip-flop. So we're going to see how it's going to propagate through some of those transistors that are in the D flip-flop. I'll then discuss why violating the setup and hold time of the flip-flop causes a metastability event to happen. After that, I'll talk about why the metastability is bad, what it does to our digital logic, and then in a part 2 video, we'll discuss how to remedy metastability, how to prevent it, and how to take down the chances of a metastability event happening. All right, so the master-slave D flip-flop we have pictured here. Now, usually when you're reading about the flip-flop in textbooks, you'll see it implemented with NAND gates or other sorts of gates. But when it's actually etched into the silicon, they want to bring down the transistor level. And so how it's implemented in silicon is as pictured here. It is simply some pass gate transistors to some inverters that are feedback looped into themselves. That makes up a latch, and then it's 2 latches that make up the D flip-flop. So again, some of the bullet points here. Closed feedback loop. You have 2 inverters, and then it feeds back into the first. That will store your value. It'll go 1, 0, 1, 0, 1, 0, 1, and it just circles and cycles, storing the value indefinitely. We have pass transistors that are going to open and close parts of the latch here. So you have the pass transistors that are going to bring in a value, and then you have a pass transistor that's going to allow the value to cycle in on itself. And then we have a master-slave latch configuration here. So this will hold your bit for 1 clock cycle. How that works is you'll have a pass transistor, and let's give an example that the clock is at 0. That leaves this open, this closed, and this open. So with this open and this closed, you've got these 2 cycling back and forth, and that'll give you the output from the prior edge-triggered store. You then have a setup that brings in your D value and then stores it, and it keeps it right here until that positive edge of 1, closing this, opening this, allowing this value to cycle, essentially grabbing it at the positive edge, and then at 1, this opens, this closes, and it allows that stored value to pass through the slave. And then once it hits the 0 again, the slave clocks in that value, closing this, opening this transistor, and then cycling and outputting it for the 0 of the clock cycle, allowing the value to be output for a whole clock cycle. We then have setup and hold time requirements that are intrinsic to how you are designing this D flip-flop. All right, so now we're going to take a peek at what causes metastability. And this is a concept everybody learning digital logic learns, and that is violating setup and hold time of your D flip-flop. And what violating the setup time means is that your data value coming into your D flip-flop needs to be held constant for a time before the edge trigger. And the hold time is the amount of time that it needs to be held constant after the edge trigger. So in our example here, we are triggering at the positive edge of the clock. And so at the 0 volts, we have a positive edge trigger event, and our value is held constant for the setup time and the hold time. We won't have a metastability event happening here. Up at the 5 volts, we have a positive edge happening of the clock, and we see that the data line is held constant for the setup time and the hold time. We don't have a metastability event happening there. Now, this is a very exaggerated example, but what we've got here is at a positive edge of our D flip-flop, we are transitioning from 0 to 1, and that is happening in the window of the setup time and the hold time. In this example, it's very exaggerated. Typically, that happens within just the setup time or the hold time. The transition is not as drawn out as this. But here, we have what could cause a metastability event. And for this example, the positive edge is clocking in at 2.5 volts. So we're going to remember that, and we're going to bring it into our next slide. And we're going to see how that 2.5 volts is going to propagate through our D flip-flop. So we've got the D flip-flop pictured here. And again, what stores the value is 2 inverters that are feeding back into each other. And that cycle will store the bit indefinitely. What we've got here is an implementation of the inverter using CMOS technology, and that's typically how it's implemented in silicone. You can have other technology implementations of the inverter, but we're going to worry about the CMOS. So this is a transfer chart of when you are inputting a voltage, what is the inverter going to output? So you've got voltage in, voltage out. So let's just use an example. If 3 volts is coming in and charging the gates of the transistors, you're going to be outputting near a 1 volt. If you have maybe 2.75 volts, then it'll output 2 volts. In standard operation, Vn will be 5 outputting a 0, or you'll have Vn be a 0 outputting a 5. So if you have 2.5 volts coming in, then we'll go up and it'll be outputting 2.5. And if you have these in series with one another, then that 2.5 is going to come into the next transistor or the next inverter, and then it's going to be outputting 2.5. So what we've got basically is once it triggers in 2.5, 2.5 is going to propagate through the closed loop of these 2 inverters. Now, what can happen is maybe there is crosstalk between different wires in the silicone, and that's a concept that we don't have to get into. Temperature differentiations, maybe imperfections in the silicone can change this transfer chart, and it can shift it left or right. So if we are inputting a 2.5, instead of a 2.5 being outputted based on imperfection, temperature, crosstalk, it'll output maybe a value that is this graph shifted. So maybe it'll be outputting then 2.75. Then 2.75 is going to come into the next inverter, and so we'll go slightly up to 2.75, and we can see that that will output us maybe at 1. Then 1 will go into the next inverter in the loop, and from 1 we get a near 5 value, and then if it goes once again to another inverter, 5 being inputted in will bring us to 0. And that's the snapping effect of these inverters snapping a value, or maybe it's referred to as the settling of a metastability event. And now with that settling of the metastability event, it's very random what the value is going to settle at. Who knows if that imperfection is going to tick, or the temperature is going to be up or down, or when maybe the crosstalk is going to happen. But it's very undeterministic what the value is going to settle to be. It could settle to be 1, it could settle to be 0, or it could settle to be a value in between, 2.5. Now, another thing that can happen with this settling is if you have 2.5 being propagated through this cycle, you then have the output of Q going through 2 more inverters. Maybe these 2 inverters are what snap or settle the metastability event, and it snaps it to a 1. But these 2 are still cycling 2.5. Maybe then in the next cycle, these 2 transistors or inverters are going to snap it to 0. Maybe it snaps it to an indeterminate value. Through every cycle, the output Q could be oscillating between 1, 0, 1, 1, 0, 1, 0, values of indeterminate in between. And the biggest issue is if the inverters don't settle the metastability event within the clock cycle time. And what will happen is the metastable erroneous value, which will randomly and undeterminately be either 0, 1, or a transition value between that, between 0 and 5 volts, that's going to propagate all the way through your logic after the D flip-flop, and then coming up to the next set of registers, set of D flip-flops, or also referred to as the next pipelining stage, it is going to then propagate even more metastable or erroneous values into the next set of registers. And that's something we don't want to happen. We want to create very deterministic machines, and adding in metastability, as you see, causes craziness. We can't determine what the value is going to be. Is it going to be 1, 0, or something in between? Alright, so let's take a peek at why violating the setup or the hold time of the flip-flop causes metastability. So in the case of the setup time is the time that the D input needs to be held constant before the edge trigger. And the reason it needs to be held constant before the edge trigger is because the D input needs time to propagate through each of these inverters to then be charged and ready at this point for the edge trigger to open this gate, close this gate, and register in the value that it's intending. If it's violated, the charge could go from 0 to 1, charging up to 2.5 maybe, and then clocking in that 2.5, causing all the issues we discussed in the prior slide. We don't want that. Now we've got the hold time. The hold time violation is a little different. These pass gate transistors are created from 2 transistors, one of the N-type, one of the P-type. Now they are being driven by the clock and the inverted clock. The inverted clock is created by passing the clock through an inverter, and that causes a propagation delay. So the clock and the inverted clock don't tick at the exact same time. So the clock will tick first. In the case of here, the clock will close this transistor first, and then a moment later it'll close the inverted clock. The hold time is just the time ensuring that both of these transistors are closed, meaning that the value after that time period, it's not getting or charging any of the inverters in here. That's why we need to hold the value constant at a time period after the positive edge of clock. So thank you folks so much for listening to this video, and I hope I was able to demystify the metastability and what it is, and just giving you folks a conceptual understanding of it. So talk to you later.